On physics class about current electricity. In the first part we have learned about that of what Kirchhoff's law of electricity, and then Western Bridge we have learned about that. And in the last part and second part or last part, you can see this, we will try to learn about the application of that Western Bridge and Kirchhoff's law. That means for that we will have to learn about the meter bridge and then the potentiometer. Okay, now in this meter bridge, what is this meter bridge actually? Meter bridge is nothing but this is a bridge where the Western Bridge can be applied, and we can find or we can determine a non-resistance with the help of that some non-resistance. In terms of non-resistance, you can see. So meter bridge is based on the principle of this Western Bridge. Okay, so when the bridge is balanced, that means when the opposite vertex of the quadrilateral so form the by 4 resistance, what happens when the opposite vertex are equal, then we know that the ratio of on the one side will be equal to ratio of the resistance on the other side, right? That bridge we call it as what Western Bridge, right? Now what is this meter bridge? Let's try to find it out, and let's try to learn it. Meter bridge is nothing but this has a 1 meter length resistance wire, okay, placed like this. 1 meter length means it is of 100 centimeter, okay, 100 centimeter resistance wire, and through this we need to connect it to the source of EMF like this. This side is the positive terminal, this is the negative terminal. Through a key we connect it to these two ends of the resistance wire AB, and there are two gaps here like this. We call it this as left gap and this as a right gap. So onto this left gap we need to put a non-resistance from a resistance box, and onto this right gap we need to put an unknown resistance which is denoted by X. And through this, okay, through this middle point of this R and X, you can call it this as you can connect it through here through a galvanometer to a jockey, and it may slide this jockey onto this resistance wire. Don't press it very hard while sliding, okay, otherwise it will change the cross-sectional area of this resistance wire. Now this is just like the 4 resistances, okay, so as to form the quadrilateral of 4 resistance, okay, onto the sides of a quadrilateral. So this will act as P, this will act as Q, and from here to here with this length, okay, if the null point is obtained here at this point J, then we can take it this as L centimeter. And if it is L from here to here, if it is L, that means from the length A to J, if it is denoted by L, then what happened, this remaining JB, the length JB will be equal to what, 100 minus L. Why? Because all this total length of AB will be equal to 100, so the remaining 100 minus L will be on this side JB. Got it? Now how to apply this? Now this meter bridge is having just to find out the null point. By sliding this jockey over to this resistance where we need to find out the null point. Null point means what? Where there is no deflection in the galvanometer. When there is no deflection in the galvanometer, that means there is no current passing through this galvanometer. In that Western Bridge we take it that Ig equal to 0. So when there is no current flowing here, that means the potential at this point and at this point will be of same potential. Okay, the difference of the potential here at these 2 points will be equal to 0, means what? Potential here and the potential here at this point, they are of same value. And so as the potential difference is 0, no current will be flowing through the galvanometer, and in that case what happened, we will call it this bridge as a balanced bridge. Now this will act as one resistance, from here to here will act as another resistance, from here to here this X will be acting as a non-resistance, and from J to B being resistance where this will be acting as a resistance. Okay, So these four resistance, we may think that these are connected on to the four sides of a quadrilateral. You can take it in that way. Now when the galvanometer is mat zero, that means when the galvanometer is mat zero, the galvanometer current I mean is mat zero, that means the potential, as I said, they are same. And we can also find out this unknown resistance by using that Metre Bridge principle. We can find out this resistance, unknown resistance X. So R by X will be equal to what? Suppose if the resistance per unit length of this resistance wire, suppose if it is denoted by K, then it will be K times L, the resistance of this AJ, I mean of this length L. The resistance of this part AJ will be equal to K times L, where K is nothing but the resistance per unit length of this resistance wire, okay. And the resistance of this JB will be equal to similarly 100 minus L times what? K. Got it? So what happened? Your R by X will be equal to KL times K times L divided by K times of 100 minus L. So when you cancel K, then you will get it as what? Let me do that one for you. Now see this R by X, okay, R by X, we can write it as R by X like this. This will be equal to what? Where K is nothing but the resistance per unit length of this potentiometer wire. So the length, if you know this length AJ, then K times L into L will be the resistance of this part AJ. So divided by resistance per unit length times what? 100 minus L. This will be the resistance of that part of what? JB. So if you cancel K, then what happened? By simply knowing this L, the balancing length, okay, of this null point, by knowing this, simply this balancing length, you can easily find out this unknown resistance in terms of this known resistance from the resistance box, okay, and this length, in terms of that you can find out what? Simply your unknown resistance, okay. This is the way how this Metre Bridge is used, just to find out the unknown resistance by applying your Metre Bridge, okay. That is how it is coming up here like this. So R by X will be equal to resistance of this AJ. RAJ means resistance through this part divided by resistance through this JB, so RJB. So if you do that one, then it will be equal to like this, as I said. KK, after cancelling the length, AJ will be equal to L, JB will be equal to 100 minus L. Got it? So therefore your X, okay, your X can be what? Expressed as R times of 100 minus L divided by L. So by knowing your R, okay, non-resistance from the resistance box, and the balancing length, if you know these two, then unknown resistance can be found out, okay. So your resistance here, if you take it this as a length, then resistance through this part is directly proportional to the length, okay. That is how we just do it, that KL, okay, that one, K times of this AJ, that means K times into L, K times L. So K means what? Resistance per unit length. As length increases, resistance will also increase. That is what it means here, okay. Now let's go to the potentiometer. So potentiometer is also a device where the principle used in the potentiometer is that the potential difference across any 2 points onto this potentiometer wire is directly proportional to its length, okay. If you take any 2 points onto this potentiometer wire, okay, then what happened? The potential difference between any 2 points onto that potentiometer wire is directly proportional to its length, okay. Here let's take it this as a potentiometer, okay, and these are the potentiometer wire, okay, from starting from A, then it comes like this, okay. This part is nothing but these are the thick copper strips, okay, or metal strips, you can take it. Got it? So this is of 1 meter length, another 1 meter, another 1 meter, 1 meter, like that. So if it is marked as 0, then this will be 100 centimeter, 100 centimeter, 200, 300, 400, like this. So in our laboratory we may find this as of 400 or 500, or you may also find with what 1000. That means this potentiometer wire may be of 10. Okay, so more the length, what happened, more the number of potentiometer wire, longer will be the potentiometer wire, right? So longer will the potentiometer wire, then the potential gradient will be lesser the potential gradient, more sensitive is the potentiometer. Got it? So you have the advantage of taking what more potentiometer wire. Okay, potentiometer of more potentiometer wire will have what more sensitivity. Got it? Sensitivity is equivalent to that of potential difference divided by the total length. We call it that potential difference here divided by the total length. So longer the length, lesser will be the potential gradient. Lesser is the potential gradient means what? Higher is the sensitivity of that particular potentiometer. Okay, so now let's see the circuit diagram for this to find out that principle of the potentiometer. Okay, now let's take it, these are the two end points of the potentiometer wire of a potentiometer. Okay, now let's try to connect the source of EMF to this end. Okay, this is the driving source. Okay, main driving source of EMF with positive terminal here, negative terminal here, like this. This positive terminal should connect to one end of the potentiometer wire, and the negative terminal should connect to the other end through an ammeter and a rheostat. Okay, negative terminal of the battery, so this side should be of the negative terminal of the ammeter, this side should be the positive terminal, and it will go in that way through a key. Okay, why this rheostat is placed? Rheostat is placed here in this circuit so as to adjust the amount of current flowing through this potentiometer wire. Okay, now wherever the potential the positive terminal of the battery is connected to that end of the potentiometer wire, that point where positive terminal of the driving source is connected, we should assume that that point as a starting point. Okay, so we have to assign 0 for that one. Got it? And just to have that potential difference between any two length, let's try to use one voltmeter here. So here this is positive, so this side should be also positive terminal of the voltmeter, and the negative terminal will be connected to a jockey. Okay, now let's see if this is of length L centimeter, that means from here A to J it is of length L, then we know that the potential difference here, see, if this is of 12 volt, for example, if the source of EMF is 12 volt, then here will be also 12 volt, right? Got it? So this 12 volt, the potential here, it will be treated as 0 here, or rather the potential difference, you can take it here, the difference here is 1 volt. If you increase the length, it will be of 2 volt. From here to here, 3 volt, 4 volt, 5 volt, 6 volt, between these 2 points, like this. You can take it in that way. It will be of what, 6 volt somewhere here. Then the potential difference between this point and somewhere here, it will be 7 volt. Here and here it will be 8 volt, 9 volt, okay, 10 volt, like that, 11 volt, 12 volt, like that. Got it? So the potential drop is there. So with the increase in length, the potential difference will also keep on increasing. Okay, so as the key is closed, what happens, current will start flowing like this. Got it? And it goes back again to the source of EMF. So what happened, this principle, okay, that we know that V is equal to IR from Ohm's law, right? So I, if the current flowing through this potentiometer wire is kept constant by adjusting through this rheostat, and it will be seen from the ammeter also. If you keep this current flowing through the potentiometer wire constant, then this portion of the resistance, if you take it as R, then it will be equal to what? Potential difference across these 2 points. That means A and J will be equal to IR, where R is a resistance across this length, okay, AJ, because your potentiometer wire is nothing but this is a resistance wire, okay. So this part will have some resistance, and let's take it that part of the resistance of this length AJ will be denoted by R. And we know that resistance R is directly proportional to the length and inversely proportional to the cross-sectional area, right? So R will be equal to rho L by A, where rho is nothing but the resistivity of the material of this potentiometer wire. So if you do not change this potentiometer wire, then as long as potentiometer wire is not changing, then what happen? Your rho and its cross-sectional area will remain constant. So you need to take a uniform cross-sectional area of this potentiometer wire. So if this potentiometer wire doesn't change, its resistivity will not change, its cross-sectional area being uniform, it will also not change, and as I told you that the current is kept constant, then what happen? I will not be also changed. So your I, rho, A, these are all constant. So if this part is constant, then your V will be directly proportional to the length L of the potentiometer wire, where there is a null point, okay, right? So your V will be directly proportional to what? L. If you take it all those constant as K, then it will be equal to V equal to KL. So we can write V is directly proportional to L. So mind you, again, in this V directly proportional to L comes from where? From the conditions that current is kept constant, okay, resistivity of the material is also constant, no doubt, and cross-sectional area of this potentiometer wire is also constant, or rather you can say uniform, okay, uniform cross-sectional area. Got it? So then what happen if we try to express this? Then V by L is also a constant. We can say V by L is a constant. So that means what? Your potential difference across any 2 points on the potentiometer of any length of wire is directly proportional to what? Its length. The potential difference between any 2 points, okay, on the potentiometer wire of any length will be directly proportional to that length of the potentiometer wire between that 2 points, okay. That is known as what? The principle of potentiometer. Now if you try to draw the graph between the potential difference and the length of the wire, then we know that as these two are directly proportional, the graph will be a straight line as shown here. So V along y-axis, L along this x-axis, then you will find the graph as straight line passing through the origin, right? So this is all about the potentiometer and its principle, and let's try to learn about the uses of the this potentiometer, okay, by using this principle and that of the Western bridge, okay. Now here what happened in this potentiometer, there are 2 applications. One is in finding the ratio of the sources of EMF, or we can call it that as comparison of EMF, and the other one is for finding the internal resistance. So for comparison of EMF of 2 primary cells, let's try to have this equation. This was what figure? This was a figure that we did, right, by connecting to the source of EMF, and we take it that one current will be flowing here like this, okay. Just to compare 2 primary source, we should have 2 source of EMF. Now let's take it for first for E1, and suppose this E1, so here E1 is connected here with the positive terminal. Mind you that the positive terminal of the driving source and the cells of whose EMF are going to be compared, their positive terminal should be also connected at the same point. So positive terminal of the driving source, positive terminal of the source of EMF, of whose EMF are going to be compared. Their positive terminal should be connected at same point, and that same point should be the starting point of the potentiometer wire. Okay, we will mark it that as 0. So what happens when this cell E1 is in the circuit? Then as this is having some EMF, what happen, each EMF will be equal to K times this length AJ1, right? AJ1 is the length of the potentiometer wire, and K is nothing but the resistance per unit length of this potentiometer wire. Got it? So what happen if current I is flowing through this potentiometer wire? Then your E1 will be equal to what? Your E1, what is wrong? So your E1, this will be equal to what? Current flowing through the potentiometer wire is I, and if you take it this as the resistance, okay, then you can mark it as R A J1. That means resistance across this length or through this length A and J1. So if your AJ1 is denoted by a length, suppose L1, then we can name it this as I, okay, then rho L1 divided by its cross-sectional area. Got it? So if you take it all this as a constant, this part, then what happen, you can name it this as some constant. Let's take it as capital K constant times L1, like this. Got it? Clear? So your E1 will be equal to K times L1. In the next case, if you are taking what, if you are taking your second, say this is the length L1. So when I say length L1, it should be from there up to here, okay, not from here. In my diagram I have shown L1 here, but this length should be starting from O, or rather 0, I mean A, starting from A, which marked as 0 here, and it will be measured up to here. Got it? Now if another cell of whose source of EMF is also denoted by E2, if you connect it here like this in a similar way, then if the null point will be somewhere here, then this length from A to J2, from A to J2, that means A J2, this length, let's take it as L2. Okay, if it is of L2 in a similar way, then your EMF E2, will be what? It will be similar to the previous equation. Then your E2 will be equal to what? K times of what? L2, where L2 is the what? Length from A, starting from here to J2. Okay, this will be the length denoted by what? L2. Got it? So if you divide these two equations, then it will be like this. K will be cancelled. Got it? And then what you will have what it is as in this way. Got it? Your E1 by E2 will be equal to what? L1 by L2 in this way, right? So by simply what, knowing the balancing length L1 and L2, you can compare the EMF of these two primary source, that means E1 and E2, right? That is what. So let's see step by steps that what it has been written here. Okay, now you will see that the balancing point is obtained for the cell when the potential at a point on the potentiometer wire is equal and opposite to the EMF of the cell. Now I told you that the potential drops, okay, is there all over this length, right? When length increases, the potential difference increases. So whatever the EMF there, okay, and the potential drop, if they are same, then there will not be no current flowing through the galvanometer. So we are trying to find that conditions where there is no deflection in the galvanometer. We call it that point as null point. Okay, when there is no deflection in the galvanometer means what? The potential at the tip of the jockey and the potential at the particular point on the potentiometer where they are same. So if their potential are same, then no current will be flowing. So what happened? Your EMF E1 will be equal to the potential difference at these 2 points. Got it? In that way we can find it out. So this is what I have already told you. Okay, so your E1 will be equal to potential drop across A and J1. That is what it will be equal to I, current I flowing here, rho times L1 by A. Got it? That this is what, as I shown you by writing there on the board, right? And E2, when you use this second cell, E2 can be also expressed in that way. So your E1 by E2 will be equal to what? L1 by L2. The balancing point we obtain on the potentiometer where if the fall of the potential along the potentiometer where is less than the EMF of the cell to be measured. Okay, here what happened? We need to note down that this potential drop, okay, across this potentiometer where that should not be less than the EMF of the cells to be compared. Okay, that means your E, capital E, must be greater than either of the EMF of these two cells, okay, to be compared. Your E must be greater than E1, must be greater than also E2. Got it? The working of the potentiometer is based on the null deflection method. That means null point finding. Okay, null deflection method means no deflection method. Got it? Yes. So the resistance of the wire becomes infinite. Okay, the resistance of the wire becomes infinite. Then what happened? The potentiometer can be regarded as an ideal voltmeter. Okay, in the case of voltmeter, what happens? Some resistance of the galvanometer. Okay, your voltmeter is rather a galvanometer. Okay, so inside that galvanometer, which is converted into what? Voltmeter, some resistance is there inside it. We call it as galvanometer coil. So likewise there will be a voltmeter coil in it. Okay, and it has its own resistance. But here by using your potentiometer, and we are trying to find what the potential difference. This potential difference, as no current is drawn from the cell when there is a null point, potential same, so no current drawn, so the potential difference across this cell we will call it as EMF, right? So this EMF is the actual measurement of potential difference. Potential difference is measured by what? Voltmeter. So we can call it this potentiometer as an ideal voltmeter. Got it? Now let's see the second part or second application, just to find out internal resistance of a cell. This is also similar to the previous circuit, but the slight modification is there. Only one cell will be there, and when this jockey is placed here, let's take it that this point J1 is the point where there is no deflection in the galvanometer. So your EMF E1 will be equal to what? I times the resistance across these A and J. So we can indirectly name this E1 equal to what? K times of L1. Okay, where K is that constant. Okay, this L1 is from where to where? From A to J1. Okay, and when we use this another small resistance connected in parallel to this source of EMF, when key K1 is closed, then what happened? Let the null point be obtained at this point J2. Now naturally, as some current is drawn from this cell E1, its potential difference here will be less, and so it will be coming at the shorter length of the potentiometer, where the balancing point will be at the shorter length from this J1. Okay, so let this be shortened somewhere here, and let this J2 be the balancing point when your shunt resistance, that means small resistance, connected in parallel to this source, primary cell E1 is connected in parallel to it. Okay, and that balancing length, let it be denoted this length AJ2 by L2. Then in this case, as some current is drawn from this cell E1, in this case we will not call it as what EMF, rather we will call it as potential difference of this cell E1. Okay, and let that potential difference of this cell E1 be denoted by V1. Then what happened? Your V1 will be again equal to what? K times of what? L2. When this sun was not there, only when EMF E1, cell E1 was there, then your E1 will be equal to what? E1 will be equal to I, or rather K, let's call it as K times of L1. We will not write the whole equation. Okay, so your E1 will be equal to what? K times of L1, where your K is nothing. Your K will be equal to what? I rho divided by A, where I is that constant current flowing through this potentiometer, where rho is the resistivity of this potentiometer wire, and A is the cross-sectional area of the potentiometer wire. Okay, when all these are kept constant, then we can replace it by K. Now in the second part, when you connect a shunt resistance parallel to this cell E1, then what happened? The balancing point was obtained at the point J2 of balancing length L2. Okay, in that case, as some current is drawn through this shunt resistance, we will not call it as EMF of the cell E1, rather we will call it as potential difference of the cell E1. Okay, and that is denoted by V1, and this will be equal to the potential difference across this length AJ2, that will be again equal to K2. Okay, no need of K2, it will be K only, where because this is a constant. Okay, as long as you are not changing the potentiometer, where then what happen, you will have this as what? K, and the balancing length, let's denote it by L2. So what happen if you try to find out this E1 by V1, then you will get it as what? You will get it after cancelling K also. Got it? After cancelling K, you will get E1 by V1 equal to what? L1 by L2. So this relation, when we try to find out that internal resistance, we know that internal resistance is equal to what? E by V, okay, minus 1 times of the external resistance. In our case, the external resistance is S, shunt resistance. Okay, so in our case here, this is the actual formula. Here it may be denoted, the actual formula may be denoted by R, the external resistance. Okay, in that external resistance it will be R like this. Got it? But for us here in this particular topic, your E will be denoted by E1, and V will be denoted by V1, and your R will be denoted by S. Got it? So what happened after finding that E1 by E2, which will be equal to L1 by L2? So by taking that balancing length, okay, then you can easily find out by using those non-quantity of the balancing length and the shunt. You can easily find out the internal resistance. Got it? So likewise, you can easily find out all those things. Okay, so let's try to learn those, whatever it is written here, step by steps. It will be all here coming in this whatever I have told you. So this is about your E1 when K1 is open, when there was no such resistance, it was only E1 there, and the balancing point was there at J1. with the balancing length L1. So your E1 will be potential difference across these 2 points. VA J1 means potential difference across these 2 points. That will be equal to I times R. R is equal to what? Rho L1 by A. Got it? When K1 is closed, when this is closed, some current is drawn, okay, from the cell E1 to this external resistance S. Your S is, why we call it S? Because this is shunt resistance. We may call it E1 as shunted. When shunt resistance means small resistance, okay. So the potential difference here between the two electrode, we will not call it as EMF. Why? Because some current is drawn from it, so we will call it as potential difference. So potential difference of the cell E1 when K1 is closed, the balancing length will be shorter, as I said, and the balancing point is somewhere here J2. So likewise, potential difference between A and J2 will be the potential difference of this cell E1. So your potential difference B1 will be expressed as like this. So E1 by B1 will be equal to L1 by L2. Okay, and so in the next equation, if you put that formula, okay, that formula R is equal to E1 by B1 minus 1 all into that external resistance. By putting this E1 by B1 here as L1 by L2, then you will get it. Okay, so by simply knowing the balancing length and the shunt resistance S, you can easily find out the internal resistance of this given cell. Got it? That is how we can find out the internal resistance and what compare the EMF of two primary cells by using potentiometer. Got it? With that, we will come to the end of our today's class. Okay, thank you.